Class 11th Chemistry. We were discussing Unit 7 Equilibrium, and in this video we will discuss about ionization of acids and bases and ionic product of water. First come to ionization of acids and bases. Strong acids like perchloric acid HClO4, hydrochloric acid HCl, hydrobromic acid HBr, hydroiodic acid Hi, nitric acid HNO3, and sulfuric acid H2SO4 are termed strong because they are almost completely dissociated into their constituent ions in an aqueous medium, thereby acting as proton donors. Strong bases like lithium hydroxide LiOH, sodium hydroxide NaOH, potassium hydroxide KOH, cesium hydroxide CSOH, and barium hydroxide BaOH twice are almost completely dissociated into ions in an aqueous medium, giving hydroxyl ions, that is OH minus ion. According to Arrhenius concept, they are strong acids. It means these are the strong acids. And bases, these are the bases, strong bases. As they are able to completely dissociate and produce hydronium ion, H3O plus, or we can say H plus ion, and OH minus ion respectively in the medium. In terms of Bronsted-Lowry concepts of acids and bases, strong acid means a good proton donor, and a strong base implies a good proton acceptor. A strong acid dissociates completely in water. The resulting base formed would be very weak. That is, we can say strong acids have very weak conjugate bases. For example, these are the strong acids, good proton donor, and their conjugate base are weaker base than water. Okay, like perchloric acid, its conjugate base is ClO4 minus, hydrochloric acid Cl minus, hydrobromic acid Br minus, hydroiodic acid I minus, nitric acid NO3 minus, sulfuric acid HSO4 minus. Okay. A very strong base would give a very weak conjugate acid. On the other hand, a weak acid, say Ha, is only partially dissociated in aqueous medium, and the solution mainly contains undissociated Ha molecules. Typical weak acids are nitrous acid HNO2, hydrofluoric acid HF, and acetic acid CH3COOH. It should be noted that weak acids have very strong conjugate bases. Okay. For example, NH2 minus, O2 minus, and H minus are very good proton acceptors and thus much stronger bases than water. Certain water-soluble organic compounds like phenolphthalein, I think you are familiar with this word, this is one acid-base indicator, and bromothymol blue behave as weak acids and exhibit different colors in their acid, that is in HIN form, and conjugate base, that is IN minus forms. Okay. If you are familiar, phenolphthalein, this is colorless in acidic medium and it gives pink color in basic medium. Okay, actually this is the acid base reaction. When this is acid indicator is represented like HIN and its suppose color is A. Okay, and when this will dissociate to give I minus. Okay, that is its conjugate base. Its color will be B. So we can say color A is different from color B. Clear? Such compounds are useful as indicators in acid-base titrations and finding out H plus ion concentration. Okay. Now what is this acid base titration? This is your practical part. Okay. When we discuss the practical, we will discuss about this titration. Ionic product of water. Water is acting both as an acid and a base. We have discussed in the previous video. That is, if water is treated with NH3, okay, in this case, water donates the proton to NH3 and itself convert into OH minus ion. Okay, so this is acid. But when water is treated with HCl, in this case, this water gains the proton from HCl and this will convert into H3O plus. So this is proton acceptor, that is base. This can also be understand if we consider only the water. So we can say there is a self-ionization of water. In pure water, one H2O molecule donates proton and acts as an acid, and another water molecules accept a proton and acts as a base at the same time. And this self-ionization of water can be represented by this equation. H2O, one molecule, this is H2O, another molecule. Now, this is acid. Okay, acid means proton donor. So it donates the proton and form its conjugate base OH minus I. Okay, and this is another molecule of water which accept the proton, that is base, and this will convert into its conjugate acid H3O plus. And for this we can write this dissociation constant. K is equal to, again, concentration of products in numerator and concentration of reactant is in denominator. But we already discussed that concentration of water, that is pure liquid, omitted from the denominator as water is a pure liquid and its concentration remains constant. So this concentration of H2O is incorporated with the equilibrium constant to give a new constant Kw, which is called the ionic product of water. We can write this. This is constant. So this constant and this K, these two constant, this will give the new constant Kw, and this Kw is equal to the product of concentration of hydronium ion and hydroxyl ion. Okay, so we can write Kw is equal to this one, or either H3O plus is obtained from H plus. That's why we can also write this Kw is the product of concentration of H plus and OH minus ion, and this is called ionic product of water. At 298 Kelvin, if we have pure water, then concentration of hydrogen ion is 1.0 into 10 to the power minus 7 m, capital M, mole per liter. And as a dissociation of water produces equal number of H plus and OH minus ions, the concentration of hydroxyl ion, that is OH minus ion, this is equal to concentration of hydrogen ion, and we already discussed concentration of hydrogen ion is equal to 1.0 into 10 to the power minus 7 m. Thus, the value of Kw at 298 Kelvin, we can write Kw is equal to concentration of H plus ion multiplied by concentration of OH minus ion, and both have the same concentration, that is 1.0 into 10 to the power minus 7 at 298 Kelvin. So we can say this 1.0 into 10 to the power minus 7 square. So this is 1.0 into 10 to the power minus 14 m square, or simply we can say Kw, this is equal to 10 to the power minus 14. Okay. The value of Kw is temperature dependent as it is an equilibrium constant. And as we know, the density of pure water is 1000 gram per liter. Okay, and its molar mass is 18 gram per mole. From these two, we can find out the molarity of pure water. Okay, what is molarity? Molarity is the number of moles present per liter of solution. So That is, we can say this is concentration or molarity of H2O. This is 1000 gram per liter divided by 18 gram per mole, or so we will get 55.55 m. Okay. The ratio of dissociated water to that of undissociated water can be given as. Okay, when water is dissociated, this will give 10 to the power. We can say 10 to the power 7 mole of water is dissociated, and this divided by 55. This is the moles of undissociated water, and its ratio is 1.8 into 10 to the power minus 9, and nearly equal to 2 into 10 to the power minus 9. Its value is very less. So equilibrium lies mainly towards undissociated water. Okay. We can distinguish acidic, neutral, and basic aqueous solutions by the relative values of hydronium ion and OH minus ion concentration. If concentration of hydrogen ion is greater than concentration of hydroxyl ion, this is acidic in nature. If concentration of hydronium ion is equal to concentration of hydroxyl ion, that is neutral. And if concentration of hydronium ion is less than concentration of hydroxyl ion, that solution is basic in nature. Okay. Thank you. Subscribe my channel to get the new videos from this chapter.